All right, recording is rolling. Welcome to another Monday, another week. So let's see, big picture. What are we doing next week or so? So today, main thing is going to be a Kahoot with some conceptual questions. I'll go back and fill in some details about rotational dynamics. Make sure you guys are plenty ready for this take-home quiz you guys got. Now, next couple of days, I'm going to do rotational inertia lab with you guys. Well, I think this will probably take a couple of days. Do you guys see that PVC pipe set up back there, shaped like a T? That can spin around that vertical axis. Tomorrow, I'm going to have you guys do that. Attach some weights, let it spin. I'm going to have you guys calculate what is the rotational inertia of that T-shaped pipe system. We'll do a whole graph and deal with that. By this Thursday, I want to start the midterm review with you guys. Now, you guys do remember that I gave you guys these review questions. So I'll go over all these, which a lot of these are going to show up on your midterm. I'll probably also have some free response on the midterm. So I haven't written this yet, but I'm going to. But I'll make sure to do lots of graphs with you guys, lots of examples, really comprehensive to make sure you guys are ready for that. If you look on AP or Google Classroom, you guys are honors. Google Classroom, there are some other review pages posted there. They look like, I think I got something reaching distance here. There's one with some variables on it that I gave you guys very first day of school back in August. There is AP equation bank too, so that could be helpful, even though you guys aren't doing AP, but I mean, it's a lot of very similar equations. There's also a page that looks like this, has some good review stuff. So I have given you all those in the past, so you might still have those pages. Right? But if you need them, then they're still on Google Classroom. This Friday, your guys' Chapter 8 puzzle problems are due. Whoops, that's not you guys. This is you guys right here. Problems that look like this. Now, we have actually covered all these in class so far, so if you want to turn it in early, you always can. But I just have the due date for this coming Friday, so I'm not going to change that. So it's Friday. And then the other thing that's due is your guys' last Open Notes take-home quiz for the semester. It looks like this, says rotational dynamics, honors on it. I gave this to you guys a few days back. This is due next Monday, so you guys got a whole week to finish this, which is like plenty of time. Okay, so you guys okay so far? What's going on? Let's flash the midterm schedule up here really fast, because your guys' first midterm is this class, and that's 10 days from now on the 16th. You know what else? I haven't mentioned this yet, but I actually have jury duty on the 16th. So, I mean, you guys will have a sub, but just heads up. Okay? All right, let's look at this starter question. I got a graph here. I've got omega versus time, something to do with a turntable. Omega versus time. Now, that's like radians per second is a function of time taken along in seconds. So I can show you exactly a scenario that could pair with that graph. Got a turntable here, give this thing a spin. Hey, it's spinning some radians per second, but notice how it's slowing down until finally it slows to a stop. And that took a few seconds to happen. Ooh, that looks a lot like this graph right here. I don't know if the numbers exactly correlate to what you saw, but it would be this graph shape. It's spinning at some radians per second, and then after a few seconds goes to like 0 radians per second, comes to a stop. Okay? Now, one thing I want you guys to be able to get out of a class like this is like graph interpretation. What kinds of information can you extract out of a graph? Most directly, you could say for any particular moment, exactly how fast is it spinning? Right? Like it starts spinning at 30 radians per second, takes 6 seconds to come to a stop. But I got another couple of questions up here. How far did the turntable turn in radians during those 6 seconds? Right? Let's start with that one. Can you guys tell me what property of this graph tells you how far it turned? How many radians it turned? How about this? Think about the units on these axes. I got radians per second on the vertical axis and some number of seconds on the horizontal axis. What happens when you take radians per second and multiply by some number of seconds? What do you get? Seconds cancels. Don't you know? Some number of radians, right? Isn't that true? Right? Which is exactly how to measure the answer to this question. How far does it turn? Because you can measure that in radians. Right? And the fact that you multiply these two units together is a really strong hint that it might have something to do with area. Right? Because area has something to do with base height. Right? You guys see a nice triangle right here? Right. I'll give you guys a little bit different approach. If you guys ever take calculus, or there might be a couple of guys who are in calculus, This process is called integration, and usually how it's originally taught is that what happens if you split this up into a bunch of very tall, skinny rectangles, right? Isn't distance equals to speed times time? So you got speed times time, that might be like a tall, approximately rectangle there. Looks like it rotated a long distance during that first second, though, spinning really fast. Then the next second, it still gains angular displacement, just not as much. And then a little less, right? Until the very last second, it kind of peters out, gains a little bit of rotation, right? Okay. But yeah, the aggregate effect is just the area of that triangle. So area of a triangle, isn't that base times height divided by 2? 6 seconds times 30 radians per second divided by 2. That sounds like 90 radians, right? You guys good with 90 radians? Okay. Hey, how many revolutions would that be? It is equivalent to 90 radians. I have to divide by what? How do you go from radians to revolutions? Divide by 2 pi. Yeah, there's out there 2 pi radians per revolution. Also 360 degrees, same thing. 14.3 revolutions. So according to this graph, this thing would have turned 14.3 revolutions before it came to a stop. There's another question here. At what rate was it slowing down? That's called alpha, angular acceleration, and that's in radians per second squared. Now take a look at that unit, radians per second squared. What property of this graph is the same thing as that unit, radians per second squared? Isn't that like radians per second per passing second? Isn't that the same thing as radians per second squared? Okay, so that'd be like if you divided these units, hey, that might be like the slope of this curve. Wouldn't that be like rise over run? Right? What is the slope of this? If I decrease by 30 radians per second over a time period of 6 seconds, 30 divided by 6 is like 5, and it's going down, so it'd be negative. So the angular acceleration is negative 5 radians per second squared. It's losing 5 radians per second every passing second. Okay. You guys got that? Okay. You guys ready for Kahoot? I'm gonna switch my screen over. Play this thing. Classic. Let's see, switch the screen for the camera. Gonna get this thing going. You're seeing it? Oh, all right. Got some more players. That 7-digit pin should show up at the bottom of the screen if you're hopping in a minute late. All right. And here we go. Which has greater linear speed, a horse near the outside or inside of a merry-go-round? All right. So some of you guys got that? The horse near the outside has a greater linear speed. Let's switch over and show you guys why. So turntable. You guys remember these 3 Roosevelts? Now I'm going to park one right on the center dot right here. And then a couple more that are progressively further out. Give this thing a spin. Okay. Now, do you guys see how they all have the same turns per time? That's angular speed. So they all have the same angular speed, right? Revolutions per minute, radians per second. Right? But if I point a radar gun or a motion detector at each one of those points, see how the middle one's reading pretty close to 0? And then the further out, they're going faster, 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 the further out you go, right? So that white poster above that door right there, one of the equations it says is that linear speed is equal to angular speed times radial distance from the center. Draw a picture for some context here. We're talking about like that outside Roosevelt there would be at some radial distance of, get a measurement. So we got 0 centimeters from the middle, got about 6 centimeters from the middle, and 12 centimeters from the middle. Is that right? And the fact that the outside one is twice as far from the middle as this guy, right, means it's also moving twice as fast in a linear sense. Okay, that true? Okay. So they all have the same angular speed, radians per second, but the ones further out have a greater linear speed. Okay? On board is got Freddy. We got an angry caterpillar. Got Bertram, Melanie, and Gabby. Which has greater angular speed? Horse near the outside or one near the inside merry-go-round? Yeah, same angular speed. Remember, the first question was linear speed. One further out, one faster. This question is about angular speed, right? Like spinning, like turns per time. Another example of angular speed I like to use is the Earth. Doesn't the Earth spin one revolution every 24 hours? That's an omega value. Okay? And if you're up near the pole or if you're down near the equator, one day is still 24 hours. Okay? So everybody has the same angular speed. Now, linear speed, different story. You're moving fastest through space near the equator. Oh, Caterpillar, moving up. Got Freddie, Bertram, KC, Undercover, Alicia. If you whirl a tin can into a string and the string suddenly breaks, the can will. Yeah, fly off tangent to its circular path. All right, you guys got that? That's awesome. Just draw this out real fast because this question goes back a ways. Guys, this is Newton's what law of motion? You guys remember something called law of inertia? It's like first law of motion. Okay. So second law was F equals ma, forces equal to mass times acceleration. The third law was equal and opposite forces. But say I got this can going around and has a instantaneous speed v, like that direction, and here's the string. Right? Say I got some scissors and I cut this thing right there. Right? Isn't that can just gonna keep going straight line, like tangent to its path, right? Which would be perpendicular to where that string was at that location. Okay? So it's first law of motion, law of inertia. Oh, Caterpillar on fire! Freddie, Bertram, Alicia, Gabby. As the rotational speed of, let's say, an O'Neill cylinder increases, the apparent weight of the people inside it does increase. Probably should have given you guys more time on that, but let me just draw this out real fast, attach an equation to it. O'Neill cylinder, like the ones that you guys made hanging from the ceiling. So this ring, now it's out in deep space. There's no real gravity around. There's the exact center of this thing. Okay. But if you give this thing a spin, omega, then everybody can walk around on the inside and feel like they're walking on ground. In fact, if you know the size of this thing, you can calculate how fast you have to spin it, radians per second, so that everybody feels like Earth gravity. Right? But suppose you spin it faster. You guys remember how centripetal acceleration, and that would be the associated acceleration, right? There's a normal force on the wall, holding them all in. They reach different masses. Divided by the mass, you get acceleration. is equal to, I told you, either linear speed squared divided by r or omega squared times r. And that's more, this one's more useful for O'Neill cylinders. So here's the spin rate. Square that multiplied by radial distance from the center. You get centrifugal acceleration. The target number here is 9.8 meters per second squared. But what if you spin this around really fast, like a centrifuge? Shouldn't everybody inside feel really, really heavy? Hey, if it's spinning twice as fast, do you guys see you're gonna have 4 times the acceleration? Still 4 times as heavy? Like that. All right. Oh. Car travels in a circle constant speed. The net force on the car is going in a circle. Yeah, is directed towards the center of the curve. That force is called the centripetal force. Right? So draw this one out for you guys. Say we're in a helicopter, we're looking down. See this road. Right? I see a car that has some instantaneous speed. Maybe we're like on a cop helicopter, we're looking for speeders, like, get this speed. So we got that. Right? We're watching this guy go around a curve. Right? Now, even though this guy's speedometer might be reading the same number, he could still be accelerating. And that would be like a centripetal acceleration because his direction is changing. Right? So there's some radius of curvature here. Call this r, like radius of curvature. And the force on this car, remember, it's always directed towards the center of the circle. Force. While he's on that curvature part, right? That's the centripetal force. Centripetal force is provided by one of your classic forces, possibly the friction between the tires in the road, or if the road is banked, maybe some component of the normal force. That force is equal to the mass of the car times the speedometer reading squared divided by that radius of curvature. There you go. Okay. And that is a centripetal force. Pushing that car into a circle. All right. Got nope. Alicia on fire, top spot. Got Caterpillar, Bertram, Freddy, Vince. What is the relative gravity field along the axis of a rotating O'Neill cylinder? It is zero. I'll show you guys why. Did another O'Neill cylinder, but maybe I've got more of a top-down view of this thing now. Okay. Change perspectives a little bit. Okay. O'Neill cylinder. Okay. Here's the axis of rotation. Here's the center of this thing. Okay. Here's some people walking around because, of course, this thing is spinning about that axis of rotation. Okay. Now, what if here's going to be the new part of this. What if I throw a ladder right across the diameter of this O'Neill cylinder? Got a ladder. Throw some rungs on this thing. Rungs. Okay, like that. Could you guys imagine if you're climbing this ladder? It takes some effort to lift it, or probably do some work. You do some work lifting yourself up this ladder. Okay? But then something kind of weird happens right when you get to the center. Okay? What do you think you feel like right at the center? Here's a hint. Centripetal acceleration is omega squared times r, where r is the radial distance from the center. So like this guy here, climbing up the ladder. Okay. You see that r relative to the center would go to 0? And then it doesn't matter how fast it's spinning, it could be a centrifuge like, if you're at the center, whatever number squared times 0 would just be 0. Be floating around like an astronaut. Okay. Next question. Portsboard. Casey undercover, hopping in the top 5. Alicia on fire, still in the lead. When a wrench is slid spinning over a frictionless tabletop, its center of gravity follows. It is a regular straight line path. I did mention this briefly back on Friday. You guys remember doing that center of gravity activity with the foam board cutouts? And say you had a wrench, you slide it spinning across some surface. Suppose you did this. What if you attach an LED light right to the center of mass of this wrench, this crazy shape, and you turn off all the lights, you just watch that light? You would actually see like a point of light follow a straight line path at a constant speed, just like a constant velocity path. That would be the only point on the wrench that did that. Yeah, it sure would. Right. Got Caterpillar and Bertram picking up some points. Alicia still in the lead. If an object is in unstable equilibrium, any displacement will? Yeah, lower its center of gravity. Things tend to want to fall down, roll downhill if they can. So if it can fall, that would make it unstable, right? If it wants to fall over. Right. Ooh, Caterpillar taking top spot. Stable equilibrium, any displacement will. Yeah, raise its center of gravity. So to lift something, you'd have to apply some work to it. So it's kind of hard to lift things. So if something's already at the lowest point, be stable there. Okay. Oh, Caterpillar on fire. Got Gabby hopping in. Got Alicia, Bertram, Freddie, also in the top 5. If an object is in neutral equilibrium, any displacement will. Yeah, neither raise nor lower. Actually, I think my example for this is, here we go. Ball resting on the floor. What kind of equilibrium? Yep, you guys got that. Neutral. So imagine ball resting on the floor. If you give it a push, doesn't center mass stay the same distance relative to the floor? Right? Just the radial size of the ball. So it doesn't go up or down. Yeah, that is neutral equilibrium. All right. Picture hangs on a wall from a wire passed over a supporting nail. It is in stable equilibrium because yeah, those are all true statements. Okay, so center of gravity is right below the support, a lot like your guys' lab back on Friday. If you did bump it, if you did push it, it would have to raise its center of gravity, which would require some work, right? And then it would just want to fall back to its original position. Yeah, those are all true statements. So confirm stability. It's true. Torque. Force times lever arm. This is the original way I told you guys about torque. Remember, it's R cross F. Right? Lever R times force. Maybe I should have typed it that way. Right? R cross F. Right? What are some of these other ones? What is mass times velocity? Since you guys are about to have a midterm here, that's what quantity? Right? Momentum. Right? You guys remember momentum? Right? Which is conserved during collisions. Right? How about the yellow one? This one's a bit more obscure, but I wonder if anybody remembers this. If you push on something with a force for some time, that delivers some what to that object? Starts with an I. Like impulse, like a change in momentum. Force times time interval would be like an impulse, change in momentum. How about the green one? What is mass times acceleration? That is a force. Yeah. Usually like in reverse, right? Force on a mass causes an acceleration. F equals ma, Newton's second law of motion. Yeah, so torque is R cross F, lever arm crossed with the force. Oh, Alicia on fire, top spot. The resistance an object has to change in its rotational state of motion is called rotational. Inertia, rotational inertia. Tomorrow, I'm going to have you guys do a lab where you calculate the rotational inertia of that T-shaped pipe system back there as it's rotating about that vertical axis. Right? How about this? You ride a bicycle. It has the classic 26-inch diameter tires. Okay, it feels like whatever. Okay? Then you go buy one of those bicycles with big old tires, like 29-inch diameter tires. Really hard to get it moving in the first place. Has so much rotational inertia. Once it is rolling, really hard to stop it. Right? Really hard to change the state of motion. Has so much rotational inertia. Oh, Caterpillar back to the top. Alicia on fire. Which has more rotational inertia, a bicycle wheel like a ring, or a solid disc, same mass, same diameter? Yeah, bicycle wheel, or because it's closest to a ring. It gave you guys a huge hint here with the equations and parentheses, but you guys got that. Yeah. So it's mr squared for a point. A ring is just a series of points, so it's mr squared. Remember, the solid disc has mass distributed closer to the center. All right, you guys are good there. Alicia still on fire, Caterpillar still in the lead. When an ice skater pulls his hands in to turn faster. Oh, nice. Yeah, those are all true statements. So angular momentum is conserved, is the general approach to this. The rotational inertia decreases, so the angular velocity increases. If you guys are all on fire on all these, I'm just going to flip the screen and draw this one out anyway. So you guys remember Paul Hewitt did this with standing on a turntable, holding some masses out? Just think it's a good review question in my plans to cover. And he was spinning about, see, this vertical axis. He was spinning with some omega, right? Then pull these masses in, mass, right? And what happened to his angular velocity? He sped up, right? So omega naught, omega final, right? So this is a conservation of angular momentum. L naught equals L final. So conservation of angular momentum. Sometimes it put that's perfectly fine to answer this question. Sometimes it put sigmas, like the sum of before and after, so that you could like add up different parts if you had to. Actually, might not be too bad an idea for this one like this. Got mr squared plus mr squared for I times omega. But angular momentum is I times omega. Because this is analogous to linear momentum, P equals mv. You guys remember how linear momentum was mass times velocity? This is angular momentum. Instead of mv, it's I omega. Right? So rotational inertia times rotational velocity. Right? So do initial, final. I'm going to make up some numbers for a numerical example. I don't know how accurate these would be for like a real life example, but just make something up. Let's say you have initial rotational inertia of like 14 kilogram meters squared, and you're spinning at 5 radians per second. Maybe like this guy here, right? And then when he pulls in those masses, what happens to his rotational inertia? Has to what, increase or decrease? Has to decrease. Let's say it cuts down to like 7 for whoops. Blow this up for the camera. Let's say 7 kilogram meters squared. Hey, or you guys tell me, what is the final angular velocity in radians per second? What number has to go here? How about this? 14 times 5 is 70. So what is 7 times what is also 70? 10. Yeah, 10 radians per second. Right? Or another way you could have thought of this is that the fact that I gets cut in half, omega has to compensate by doubling. 1 and a half, 1 double to preserve that product. Yeah, that's conservation of angular momentum. That's the easiest way to explain ice skater question, anything like that. So present screen to share. We got Caterpillar on fire. Alicia, Bertram, Gabby, Casey undercover. Huge rotating cloud of particles in space gravitates together to form a dense ball. As the cloud shrinks, it rotates how? Yeah, faster, which is the exact same principle as I just drew over there with like Paul Hewitt on his turntable, the ice skater question. It's the exact same question, really. Conservation of angular momentum. Alicia on fire, Caterpillar still in the top spot. two people sit on a balanced seesaw. When one person leans toward the center, that person's end will be what? Rise, yeah. Okay, like I said, pretty good on that. Wait, switch over. This is another one I was going to draw anyway, so I'll do that. So get a seesaw. So let me get a couple of seesaws going, like a before and after type picture. Okay. I'm going to put this pivot point right at the center. Okay. And this is going to be a torque question. Torque is R cross F. And we're going to take the point right at the center to be the pivot point. Right? Whether it's like that one or that one. Right? Right? The pivot point right at the center. Right? Right, so let's throw a couple of friends on here. Have this guy and this guy. And for simplicity, let's have them the same mass and therefore the same weight and also the same radial distance from the center. Like I said. So this guy has some weight. I call it F like a force. This guy has the same weight, F like a force. And they are equal radial distances from the pivot point, R. Right? So this guy on the left is causing a counterclockwise torque, and this guy is causing a clockwise torque relative to that center point, right? See how they're balancing each other out because they got the same torque value, just opposite directions. So this whole thing's balanced. Right? It's balanced like just like that. Right. Now I'm gonna have this guy on the left lean towards the center. One tool you can get for your mental toolkit out of this class is to maybe exaggerate variables a little bit. No, if it's not obvious what the answer is right away, say, well, what if I make it even more drastic? What if, for example, instead of leaning, this guy walks halfway to that pivot point? Would he be cutting that radial value in half? If you cut this in half, this R, doesn't the torque also get cut in half? Because he has the same force. Right? His weight didn't change. Force F, right? That's the same. Right? This guy on the right has the same clockwise torque, but this guy on the left has a very small counterclockwise torque. Right? So doesn't this whole thing have to turn clockwise? Okay? It's going to turn maybe something more like this right here. Yeah, it's gonna rotate. Is it? All right, let's say this guy's in. It's gonna rise. That's the answer to that question. Say present screen to share. Gabby's on fire. To turn a stubborn screw, it's best to use a screwdriver that has a what? Screwdriver. A wide handle? Why a wide handle? Why do you want a wide handle screwdriver? This one I haven't directly covered yet, but show you guys why. Let me draw a tool that I've drawn you guys before, which is a wrench, which is a different kind of tool. So here's a wrench. Okay. Now the wrench you would want a long handle, right? Because torque is equal to R cross F. Okay. Now this wrench trying to turn this nut. You guys know that the axis of rotation would be like out of the page, like 3D. Now to simplify this a bit, got to sort of turn this. Right? Let's say there's sort of like a torque about this point because at this radial distance from that axis of rotation, call it R radial distance. So you apply a force perpendicular to that F, right? R cross F to get some torque. Right? And the longer the handle for a wrench, the more torque you're going to get. Now let's contrast that to a screwdriver. Right? So your screw going here, okay. Screwdriver. Now I'm going to grip this handle and start turning the screwdriver. There's a frictional force between my hand and the handle. Okay? But look at where the axis of rotation is. Doesn't the axis of rotation actually run exactly along the screwdriver? Like right there? There's your axis of rotation. Right? Different from the wrench. Screwdriver looks like it. And isn't this the radial distance from that axis of rotation? So again, there's a frictional force in your hand, and that will allow you to cause some torque, tau, around that because you're applying, say, like a force at the edge here. This force crossed with that R, right? And the wider the handle, the more torque you can get. If you had a handle that was like twice as wide, you get twice the torque. Okay? Even for the same force. Oh, yeah, we're good there. Oh, last question. A ring, a disc, and a solid ball with equal masses roll down the hill at the same time. Who reaches the bottom first? Yeah, the ball. Do you guys notice that the ball has the smallest rotational inertia? I'll tell you guys what to see that detail about equal masses. Turns out that the mass cancels out, which you may have guessed from one of the very first labs you guys ever did with the Hot Wheels cars. Okay. Furthermore, the radial size also cancels out. What matters is how the mass is distributed. And for the ball, it's distributed closer to its own center. So it has the least rotational inertia. So it's easiest to get it rolling. So yeah, so it'll win the race. Now, I do want to go to the winner's podium with that Kahoot, but since I'm switching over here, draw this out for you guys too. Wait, did I? Okay, for cameras. All right, let's take a look at that question. I'm going to draw this half pipe type setup. And let's have a race between this ring, this solid cylinder, like a Flintstone wheel, and this solid sphere. I'll use a bowling ball to represent. That's a pretty good approximation. So you guys remember the ring has a rotational inertia of mr squared. It's the m refers to its own mass. The r is its radial size. For the solid disk, well, it's has mass distributed closer to the center. So it has to be less than mr squared. It ends up being half mr squared. And for the bowling ball, it's even a little bit more so. It's 2/5 mr squared. Right? It's got 100% mr squared, 50% mr squared, and 40% mr squared. Because 2/5 is 40%. Right? So yeah, so it is easier to get the bowling ball rotating. Right? Here's what the motion of these three objects would look like. Here's the ring. Whoosh, 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 whoosh. And if there's no frictional losses, now you do need some static friction to induce rolling, but if there's no frictional losses, you could do that for thousands of years, just like whoosh, whoosh. Here's the solid cylinder. Whoosh, 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 whoosh. A little bit faster. Here's the bowling ball. Zoom, 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 zoom. Of course, I'm exaggerating that a bit, but you guys get the idea, right? Okay. Now, last week I sort of set this up for you. I want to remind you guys what we were doing last week, which is suppose you have a finish line down here, and not only do you want to figure out who's going to win the race, it's going to be the bowling ball. Talked about that already. But maybe furthermore, you want to figure out what is the exact speed, say linear speed, that these are going to cross the finish line. This guy has a radar gun, so a little bit big for him, but do that. What's the speed these are crossing this finish line? And you want to solve this with conservation of energy. Sum of energy initial equals sum of energy final. Where initially they start off with all potential energy, but by the time they cross this finish line, it's going to turn into, well, you'll have your traditional linear kinetic, 1/2 mv squared, but also there's some energy that went into inducing rotation. Whoops, 1/2 I omega squared, right? And the fact that the bowling ball has the smallest I value means that the smallest number of joules will route into this term, which is another hint that yeah, the bowling ball will be moving fastest across the finish line. It also wins the race. Okay. All right, flip back over. Okay, let's check out this winner's podium. We got, with the bronze, Bertram. With the silver, Alicia. And the gold, Caterpillar. And our runners-up are Gabby and Casey Undercover. All right, nice job, guys. Nice job. Under homework, there's some problems I did not assign, but I printed out that I want to go over. One of them, I have an animation for lined up. So Here we go. Okay, that's what I'm looking for. Let's take a look at this animation. You guys, actually, I meant to show you guys the still screen before I played that, but suppose you didn't see any animation yet. Right? Which gear do you think is moving the fastest and which one's the slowest? I'll narrow it down to the one on the left and the one on the right. The red one on the left and the blue one on the right. Who's moving really fast and who's moving really slow? How about that red one on the left is moving really what? Like fast? Yeah. Let's take a look at the animation. Yeah, it sure is. Right. Now one of the questions on your homework, it's number 61. I didn't assign it. It's number 61 on the printout. Does say you have a couple of gears next to each other, say a small gear next to a big gear. Can you compare their angular velocities? And obviously you see that the small one's moving faster, right? But also, can you compare the linear velocities of the teeth that are in contact, right? Is that? All right, let me switch back over to projection. Go through this one with you guys. Okay. So, say you have a large size wheel and a small size wheel. Okay. I'll even throw some radial values on here. Let's say this radial size is 10 centimeters. Let's say this radial size is 5 centimeters. Okay. And they got some teeth going all the way around. Okay, teeth. Okay. So this is number 61 from your book. Question A was compare their angular velocities. The question B, which I'm going to start with, says compare their linear, the linear velocities of their teeth. Okay? And that would be the same linear velocity. Right? So like those teeth going together like this, right? Don't they have the teeth on the left and the teeth on the right are even at the same linear velocity? Right? But question A has something to do with angular velocity. You guys remember how either linear velocity is angular velocity times radial size, or you could switch this around. Omega is v divided by r. Right? So if they have the same linear speed at their teeth, then the fact that the big one has twice the radial size, shouldn't it have half the angular velocity? So angular velocity of the large gear is less than angular velocity of the small gear. In fact, for my exact setup with 10 centimeters versus 5 centimeters, you guys see that omega of the large is exactly half omega of the small, right? Or omega small gear could be 2 times omega of the large gear, if you like thinking of it that way. Okay. How about this? If you compare their circumference values, circumference equals 2 pi r. How big is the big circumference compared to the small circumference? Is it twice as much? Yes, it is, because that's twice the radius. That's a linear relationship. So when the big gear makes one complete revolution, how many revolutions has the small gear made? 2. Like 2. Right? The other one I want to look at is number 62, videotape. When a videotape is rewound, why does it wind up fastest toward the end? So I know this is an old technology. I don't know, do you guys have parents who have like either old VHS tapes or cassette tapes? You guys ever seen some of these? Okay. It's the same basic principle. So I'm going to draw something that could either apply to a VHS tape or a cassette tape. It's got these little gears on it. Now, one of these gears is connected to a motor, and one of these is just like free to rotate. Okay? And you've got some tape wound around. Like, say wound around that way, and then press over here, and then you've got a big old diameter circle winds around. Right? So you have something that looks like that. Is it? And then there's like some reader that will like read the tape, either music if it's cassette or like some frames if it's a VHS video. Right? So let's think about this dynamic. Let's say that the motor is attached to the left gear and it rotates around once, one revolution. Think about how much tape that would pull. How far does the big gear move? A lot or a little? I think just a few degrees. For this to turn around once on the left, the big one only turns a little bit. Right? But you do that enough, and doesn't the tape transfer from the right to the left? Okay. And wouldn't that give the left one a larger diameter? So by the time it's finished with that process, be like kind of like if you take this and flip it, flip it around, it will look like this, just the opposite side. So now, effectively, I'm going to put the motor on the right one. Okay, so this is wound up to the point that most of the tape is on the side with the motor. Right? Now, if this makes one revolution, because it's probably easiest to design it, just turn constant RPM. I imagine that would be the easier ways to design this thing, like a record player. If this turns around once, doesn't this small gear have to go do like several spins? Yeah, so that's that type relationship going there. Okay. Right. Anyway, last thing I want to throw you guys today is there's a Vsauce video that says, why don't any animals have tails? So we'll just play that until the bell rings. If you want to look more into that, then feel free to. But I'm going to pause the or stop the recording right here.